All right, credit to my good friend Steve Aoki for getting us all pumped up for this next lesson on factored form of polynomials. Our learning goal is to determine the equation of a polynomial function, and given a polynomial, make a possible sketch. So we are going to be doing some graphs for this lesson. If you have graph paper, you might want to pause, grab it, and come back. Otherwise, just doing it roughly in your notes will suffice. So we're going to start out with some definitions first. Last lesson was kind of standard form of a polynomial. Now it's factored form, which looks like that. Very similar to factored form of a quadratic, except for there's could be technically an infinite number of factors, but you still have your leading coefficient a and then a certain number of factors. The degree of the polynomial is the sum of the exponents when written in this form. The leading coefficient determines the end behaviors, and the exponents indicate the behavior at each zero. So remember from last lesson, where it's in standard form, you can arrange the terms from highest to lowest, and the highest term is the degree of the function. Today they're going to be factored form, and I don't want to spend time foiling and distributing all of these to get to standard form. So the easiest thing to do to determine the degree is just add up all the exponents. And then just like the last lesson, leading coefficient determines the end behaviors. Now we're going to specifically go through several different things that happen for each exponent. So if n is 1, if the exponent is 1, it's called a single root, and it just crosses the x-axis. We'll do a little sketch beside everyone. So if it's a single root, x and y, here my function just passes right through. If it's a double root, it just touches the x-axis and then swings back, like turns back around. So if we have x and y, I just touch the x-axis, so I'm coming and then I turn back around. And I could do something going the other way as well. If n is 3, it's called a triple root, and it's called an inflection point, as we kind of teased yesterday. And an inflection point, it's going to touch, so you're still going to have a 0, but it does a little kind of wiggle. So let's just say, where it doesn't change direction, but what does happen is the rate of change actually increases or decreases. There's a little wiggle there. If n is 4, it's considered a quadruple root, which means it just touches the x-axis, but much more wide than a double root. So x and y, and it looks more like a horseshoe. So it kind of does something like that. It still only touches it once. And then from there, we could keep going. If it's 5, it's a quintuple root. It's still an inflection point, just a bit wider, and so on. If it was 6, then it would look like our quadruple root, but a little bit wider, and so on. This picture is a good visual of all the things you're going to be seeing and possibly sketching, so you might want to listen to this and then pause and copy it. But polynomial functions always have smooth graphs with no discontinuities. So polynomial graphs are never discontinuous. And then as we kind of go left to right, you can see we have a single root, just crosses it once. a double root, touches it, then turns back around. And then a triple root, an inflection point, does a little wiggle. If we move back over to the left, these kind of peaks here and here, those are maximums. And if it's not an absolute maximum, then it's called a local maximum. It's a turning point. And then over here on the right, a global maximum. It's the highest it gets. And of course, we have our y-intercept where our graph crosses the y-axis. And then these don't have arrows on them, but we could add arrows. And that gives us our end behaviors. So that gives us a visual of what we just did written. Again, I would pause it and copy this down. So our first example, we are going to make some sketches. And it says a possible sketch because we don't know exactly. So calculus and vectors is going to be focused on you making an exact graph. For advanced functions, we're going to be sketching based on knowledge we have, but not making an exact graph. So you might want to have your little chart that you made handy, or your chart that you made in the last lesson, have that handy, because that's going to help us with our sketch. So when you do this, the work I should see, so what matters is the degree. So the degree, which in this case, remember when it's written in factored form, you can add up all of the exponents. Don't forget, even though we don't write it, there's really a 1 there. And 1 plus 2 plus 3 is 6. So we have a degree 6, which is even. Next thing we care about is our leading coefficient. Which is your A value, that number out front here. Now there's nothing written there, it doesn't mean it's 0. It means it's a 1. And all we care about is if it's positive or negative. And it's positive. So based off of those two pieces of information alone, the degree and the leading coefficient, we already know that the end behaviors should be like this. That's just based off the degree, it's even, leading coefficient, and behaviors go up. Now the next thing we care about are our zeros, which we have a 0 at x equals 2, x equals 4, and x equals 6. And based off the exponents on each one of those, 2 is a single root, 4 is a double root, and 6 is a triple root. And then the last thing you want to find is your y-intercept. So how do you find a y-intercept? X is 0. F of 0 equals, put 0 in for all of those x's and do some calculator work. And you're often going to get kind of crazy numbers for these. You should get 6,912. It's okay that our graph only goes up to 10. We'll fudge it a little bit. So now we're ready to graph. First thing I would do if I were you, put your zeros on. 2, 4, 6. 2, 4, 6. And we know our y-intercept is 6,912. I'm just going to scratch out the 10. Again, we're just making a sketch. And it's perfectly okay if you do this on your test. And we know that based off our degree and leading coefficients, our end behaviors got to be like this. So, I have to do a single root, double root, triple root, and end up with those two end behaviors. It takes some practice and maybe even just some trial and error, but let's see what happens. 2 is a single root, means I go through. 4 is a double root, which means I go up to it and turn back around. And again, we're making a sketch, so you can go as low as you want with that. I touch this on my double root, turn back around. And then at 6, it's a triple root, so it does like a little wiggle. It's an inflection point. So all I'm going to do is something like that, just to show that there's a bit of a wiggle there. And that is a possible sketch. And then don't forget to label it f of x, and that's our x-axis, and that's our y-axis. So easy as that. B. Again, make a possible sketch. So we're going to go through the exact same steps. And again, I just want to stress to everybody, when you do these questions on a test, I need to see the work. I can't just see the final graph because I have no idea where you got it from. So my degree. Add up the exponents. Remember, there's a 1 and a 1 there. When it's in factored form, degree of 4, which means it's even. My leading coefficient is negative, which, based off of those two pieces of information, I know that my end behaviors are going to be like that. My zeros, I have one at -2, 1, and 3. That is a single root. That is also a single root. And 3 is a double root. My y-intercept, f of 0, put 0 in for all of those, and you should get 18, I believe. And since there's already an 8 there, I'm just going to write a 1 in front of it to make it 18. I will scratch out that 10. So already we know that's my y-intercept. X-axis, y-axis. Let's put our zeros on. -2, 1, and 3. I know I got to end up like this. So, -2 is a single root, so is 1. Okay, so that means I just pass through. That probably means that I'm going to turn back around, but I'll go through my y-intercept and come back around. I just pass through. And then 3 has a double root, so come up to it, touch it, come back down. And there is a possible sketch for f of x. Our next one, C. This looks a little bit different. This is not in factored form. That doesn't mean you can't graph it, or make a sketch of it. It means that you got to factor it. So let's go back to our factoring skills. This would be a common factor, x cubed, which would leave you with x plus 2. Oops. Pen dragged. We'll just erase that, fix it. Perfect. Now we're ready to show our work, our degree. Our degree is 4. I'm just going to write LC for leading coefficient. Most of you probably know by now. Positive. Even degree. Positive leading coefficient. My end behaviors are like this. My zeros, x equals 0 and -2. And that's a triple root, and that's a single root. Y intercept, f of 0 gets 0. All right, we're ready to make a sketch. X and Y axis. Put on our zeros, -2 and 0. That's also your y-intercept. And we know we got to do this. -2 is a single root, so we're just going to pass through it. And 0 is a triple root, meaning it's an inflection point, does a little wiggle. So we'll come down, do a little wiggle, and come back up. And there's a possible sketch of f of x. Hopefully that's making sense so far. So far so good, I hope. Not too bad. So now we're going to abandon sketching and we're going to work the opposite way. I'm going to give you some information. You're going to give me the equation in factored form. A, for a cubic, now that's important information, so I'm going to underline that. For a cubic function that has zeros at -2, 3, and 2/5 with a y-intercept of 6. So let's start out here, f of x equals, good start. A, now you're almost always going to have to find A for these. We have a 0 at -2, so when I put that into factored form, x plus 2. I have another 0 at 3, so x minus 3. And then 2/5, and it's bad form to write x minus 2/5. So you kind of got to work backwards. If you remember the patterns from grade 11 and even a little bit of grade 10, if your factors are written in like ax plus b form, this is your b and this is your ax, meaning it should be 5x minus 2. And you can double check that. If you put 2/5 in times 5, you're going to get 2. 2 minus 2 is 0. And a y-intercept of 6. So all we're missing is the a value. Now I've given you another point, the y-intercept, which has coordinates 0, 6. How do I find a value? Well, there's my x and there's my y, or in other words, f of x in function notation. So you're going to sub that into your equation for x and y, or x and f of x in this case. So put a 6 in there and put a 0 in for all your x's. Go through the math. Do all of your brackets first. Hopefully you get 12. So 12a. Divide both sides by 12. 6 divided by 12, 1/2. Now just because you found a doesn't mean your job is done. That's the hard part, but you got to put it all together to get that final mark. Remember, it's asking us for an equation. So f of x equals 1/2 x plus 2, x minus 3, and then 5x minus 2. And there's our final function. Really, you've done this process in grade 10 and grade 11. We're just expanding on it with more factors this time. B, same thing, make an equation for a quartic that has zeros at -2, order of 2, 3, 1, and goes to the point 2, 32. Quartic, that's important. Has zeros at -2. Now, order of 2, if you see order of 2, order of 3, order of 4, whatever, that's just your n. So when you see that, that just means n is 2, meaning your exponent is 2. In other words, it's a double root. Starting point, f of x equals a, and then a 0 at -2, x plus 2, but it's order of 2, so it means our exponent's 2. 3, so x minus 3, and 1, so x minus 1. And it goes through the point 2, 32. So there's your x, there's your f of x or y. Go through the exact same process. Now that I've started you off, to prove that you know what you're doing, I would like you to try this on your own. So we're going to try yourself. So pause the video, sub that in for x and f of x, and hit play again when you're ready to take it up. Welcome back. If you paused and you tried it and you feel good and you feel confident about your answer because you got a as -2. And there is our final function. So if you got that, great work. You're on the ball. C, still making an equation, but this time from a graph. Same starting point as always, f of x equals a. And let's start with our zeros. So we have a 0 right here at -3, which means our factor is x plus 3. Single root, exponent 1. My next 0 is at 2. So x minus 2. Now that is a double root, right? It touches it and comes back down. It turns. Double root. I mean, it could be a 4th or a 6th or an 8th root. We don't know. But let's keep it simple, because as soon as you start going up with like 4, 6, 8, 10, you're going to end up with large numbers. If you want to and you want to be creative, go for it. But let's just keep it simple. And then our next 0 would be 5, and it's a single root. So x minus 5. Now you need to sub in a value to get your a. Since we started with factored form, you should never sub a factor back in because it'll turn the whole thing to 0 and you'll end up with a number equals 0, which is your indicator that you messed up. So pick another nice point. A nice point that I see is right here. That's convenient. That gave us our y-intercept, which was 0 and -2. So we're going to sub that in for x and f of x, or y. So -2, put in 0 for all your x's. Use your calculator. You should get, I believe, -60. A. Divide both sides by that. Reduce. A equals 1/30. Final equation. 1/30 x plus 3, x minus 2 squared, x minus 5. As a built-in self-check, if you got a negative for your a value, you probably know you're wrong based off of this graph because the end behaviors are going to infinity, meaning it's pointing up, meaning our leading coefficient should be positive. Otherwise, it would be pointing down, going to negative infinity. That's it for lesson number 2. There's some C work. Again, make sure you double check D2L first to see if I deleted any of those questions. And that should be a good enough start. So if anybody did happen to watch this over the weekend, you have a good enough head start on Unit 2 for Monday.